You know that incredibly specific, uniquely modern frustration.
Oh, I know exactly where you're going with this.
Right. Like spending a good chunk of money on a shiny new smart gadget entirely because it's supposed to save you money, only to realize later that it is, well, actually costing you more.
Yeah, we put a massive amount of faith in the label smart.
Mm-hmm.
I mean, we tend to assume the device possesses some inherent wisdom about efficiency that we just lack.
Yeah.
So we hand over control and assume it knows best.
Exactly. You buy the thing, you mount it on the wall, and you just expect it to perform its magic. And that brings us to a really telling case from our sources today.
Right, the Hennessey case.
Yeah, a homeowner in Hennessey, Oklahoma decides to upgrade for the summer. They buy a brand new Nest smart thermostat specifically chasing those energy savings.
Naturally.
So they get it installed, they wait for the electric bill to plummet, but July rolls around, the bill arrives, and it has absolutely skyrocketed.
The irony there is just, well, the smart technology actively sabotaged the homeowner's wallet. To understand why, we have to look at the mechanics of the learning algorithm inside that specific thermostat. The device relies on a combination of near-field motion sensors and manual dial adjustments to build a data model of your preferences.
Right, it's watching what you do.
Exactly. If you walk past the thermostat on a hot July afternoon, feel a momentary draft, and nudge the dial down to 72 degrees, the algorithm records that.
Makes sense.
Do that a few times, and the system learns to prioritize your immediate comfort over any sort of baseline efficiency. In this specific Hennessey case, the algorithm basically defaulted to holding the house at a constant 72 degrees 24 hours a day, 7 days a week.
Because it learned that whenever the human interacted with it, the human wanted 72.
Right.
But here's the really critical detail. Before this homeowner bought the expensive smart thermostat, they were actually using an old, completely dumb, programmable thermostat.
One of the classic ones, yeah.
Yeah, and that old device had been hard-coded to bump the house temperature up to 78 degrees during the day when everyone was at work. It was inflexible. It didn't care if you walked by.
Right, it just did its job.
So the new algorithm effectively erased all that built-in downtime that the old basic thermostat was already executing.
It wasn't until a rigid schedule was manually forced into that smart thermostat that the homeowner's bill finally dropped, yielding an 18% reduction compared to the previous year.
Wow, 18%.
Yeah, the savings only appeared when the human took control back from the algorithm.
Okay, let's unpack this, because this deep dive is all about decoding how these devices actually interact with your HVAC system. We are pulling directly from the field notes of Dave Hartzell.
A true industry veteran.
Oh, absolutely. He's a master HVAC technician with 45 years of experience in Central Oklahoma. He's NATE certified, IGSHPA accredited, and he owns Hartzell's Heat and Air.
Which has stellar reviews, by the way.
Yeah, he's sitting on a 4.8 star rating across 276 reviews, so he has seen literally every configuration imaginable. We are combining his data with Department of Energy research to figure out how these thermostats actually save you money.
And spoiler alert, it really has nothing to do with the silicon inside the device.
Right.
It has everything to do with the hidden mechanics of the schedule. The hardware is ultimately just a switch on your wall. The financial return on investment lives entirely within the parameters you set for it.
But before we get into building that perfect schedule, we really need to address a major mental hurdle. When you hear about that homeowner holding the house at a flat 72 degrees, it's easy to look at that and think, wait, isn't it more efficient to just leave the AC at one constant temperature?
That is such a common misconception.
Yeah, I hear people use a freight train analogy all the time. The logic goes that an air conditioning system is like a heavy train. It takes a massive amount of energy to get it moving from a dead stop. But once it's rolling down the tracks, it takes very little energy to maintain that steady speed.
Right, the momentum idea.
Exactly. So they assume keeping the house at a constant 72 is easier on the system than letting it warm up and forcing that heavy train to start cooling all over again.
What's fascinating here is that the momentum analogy feels intuitive, because we see it in physics all the time with vehicles. But an air conditioning system doesn't operate on kinetic momentum. No, it operates purely on thermodynamics. Your AC is not a train trying to keep its speed up. It's a machine designed to fight heat transfer.
Okay.
Heat is constantly trying to push its way through your walls, your roof, and your windows.
And the intensity of that push is what dictates how hard the AC has to work.
Right, exactly. And that intensity is strictly proportional to the temperature difference between the inside of your house and the outside environment, what engineers call the delta T.
The delta T. Got it.
Yeah. So if it's 100 degrees outside
Yeah.
and you're trying to hold the inside at a crisp 72 degrees, you have a delta T of 28 degrees.
That sounds like a lot.
It is a massive thermal pressure gradient. The heat from outside is aggressively invading the structure. Your AC has to run constantly just to hold the line against that severe thermal pressure.
So if you let the house drift up to 78 degrees while you are away at work, you are actively shrinking the target.
Right.
Now you're only fighting a 22-degree difference.
And by reducing that delta T, the actual rate of heat transfer from outside to inside slows down significantly. It's less about the AC resting and more about allowing less total heat energy to enter the building envelope in the first place.
Which means less work later.
Exactly. Less heat entering the house means your air conditioner has less total sensible heat to remove over the course of a 24-hour cycle.
The Department of Energy actually quantified this thermal math. Their research shows that for every degree you set back your thermostat, you save about 1% of your cooling costs per 8-hour period.
Which really adds up.
It does, and if you maintain that setback, it compounds. It works out to roughly 8% savings per degree of setback over the entire cooling season.
That's huge.
Yeah, the freight train idea is completely busted. Letting the house warm up absolutely reduces the total energy consumed.
The math scales up incredibly fast once you embrace the thermodynamics of heat transfer rather than that myth of momentum.
But you know, the math on an 8% savings makes perfect sense on a spreadsheet. No one wants to live in a laboratory experiment, though.
True.
So how do you apply these thermodynamics without turning your living room into a sauna? Well, Dave Hartzell has actually mapped out a field-tested Central Oklahoma cooling schedule that threads this needle perfectly.
I love this schedule.
It's brilliant.
Yeah.
He breaks the day into 4 phases to hit that 18% savings mark without sacrificing livability. First is the wake phase, from 6 a.m. to 8 a.m. The thermostat is set to 72 degrees.
Getting ready for work, making coffee nice and cool.
Exactly. Second is the away phase, from 8 a.m. to 5 p.m. when the house is empty. The thermostat bumps up to 78 degrees. Third is the home phase, 5 p.m. to 10 p.m., dropping back down to 72 degrees. And finally, the sleep phase, from 10 p.m. to 6 a.m., where the house drifts up slightly to 76 degrees.
If we run the weighted calculations on that schedule, the efficiency becomes really clear. You have 9 hours during the day where the temperature is set back by 6 degrees.
Right.
Then you have 8 hours at night with a 4-degree setback.
Yeah.
When you compare that thermal load against a baseline of a constant 72 degrees, it yields a 17 to 19% reduction in total cooling runtime.
Wow. And he also notes a heating counterpart for the winter, right?
Yeah.
Wake at 70, away at 65, home at 70, and sleep at 66.
Right. Same principle.
Though because gas furnace efficiency scales more linearly than the complex refrigerant cycles of an air conditioner, the savings on the heating side cap out around a solid 12%.
Still, 12% just for adjusting the parameters is an incredible return on investment. The elegance of Dave's cooling schedule really lies in human physiology.
How
Well, it is designed to be invisible. During the most aggressive setback, the 78 degrees, you aren't physically in the building. And during the night's setback to 76, your body's metabolism is naturally slowed down during sleep, and the ambient temperature outside has dropped, which reduces the radiant heat load on the structure.
So you don't even feel it.
Right. Most people will run this schedule and never consciously realize the AC is operating under a lighter load.
Okay, I understand the metabolic shift during sleep, but I have to be honest, I run hot.
A lot of people do.
Yeah, trying to sleep at 76 degrees sounds like a recipe for insomnia. There are plenty of people who need the room freezing to get a good night's rest. Does the entire mathematical model just fall apart if you refuse to sleep at 76?
Doesn't have to. You just have to use targeted solutions rather than whole house brute force.
Targeted solutions, okay.
Yeah, the simplest mechanical workaround is a ceiling fan. By running a ceiling fan in the bedroom while keeping the whole house thermostat at 76 degrees, you utilize the evaporative cooling effect on your skin.
Like a breeze.
Exactly. That airflow alters the perceived temperature, making a 76-degree room physically feel closer to 73 degrees.
But if the airflow trick isn't enough and you demand the room physically sits at 70 degrees, you still shouldn't drop the entire house to 70.
No, definitely not.
Dave points out that if you have a zoned HVAC system, you can use automated dampers to drop the specific bedroom zone to 70 degrees while the living room, kitchen, and guest rooms hold at that efficient 76 degrees.
Right. The objective is to stop paying to remove heat from empty square footage. Zoned cooling is incredibly effective. But there is another mechanism that higher-end smart thermostats use to manipulate comfort without drastically dropping the temperature.
Oh, this is fascinating.
It involves prioritizing latent heat removal, or, in simpler terms, humidity control.
Dave calls this the free comfort upgrade. Smart models like the Ecobee or the Honeywell can be configured to prioritize humidity over strict temperature. But how does the thermostat actually command the AC to wring the moisture out of the air?
Well, standard air conditioners often run in short, powerful bursts. They blast cold air, hit the target temperature quickly, and shut off.
Right.
The problem is that while the temperature drops quickly, the system doesn't run long enough for the air to pass over the cold evaporator coils to actually extract the moisture.
Oh, so you end up with a room that is cool but clammy.
Exactly. A smart thermostat equipped with humidity controls alters this behavior. On a humid afternoon, it will intentionally command the AC to run slightly longer, often at a lower compressor stage if you have variable speed equipment.
Okay, so it runs slower.
Yes. By keeping the evaporator coil cold for an extended period without drastically overcooling the room, the system basically acts as a dedicated dehumidifier.
Lowering the ambient moisture changes everything about how the house feels. I mean, a house sitting at 76 degrees with a low 45% relative humidity is going to feel vastly more comfortable than a house at 73 degrees with a muggy 55% humidity.
Unquestionably.
It allows the body's natural thermal regulation to actually function. You buy a higher tier of comfort by managing the moisture, which requires far less energy than forcing the compressor to drag the sensible temperature down to freezing.
It is a much more sophisticated use of the equipment.
Okay, thermodynamics says I save money by letting the house get hot during the day. But if my house is sitting at 78 degrees when I get off work, I'm walking into an oven.
Right. Nobody wants that.
And if I force the AC to drop the house from 78 to 72 right at 5 p.m., aren't I just burning all the energy I supposedly saved trying to cool the place down instantly? The system has to work at absolute maximum capacity during the hottest part of the late afternoon.
You are identifying the problem of recovery load. Pulling a house down by 6 degrees requires massive energy if you demand it happen immediately.
It's just too much all at once.
Yeah, the equipment will roar to life, run at 100% capacity, and struggle for 45 to 60 minutes to pull that heat out of the air, the furniture, and the walls.
And you sit there sweating.
You sit there sweating, and the equipment undergoes immense mechanical strain. This is where the integration of geofencing completely solves the recovery load issue.
Geofencing, which relies on the GPS hardware in your smartphone, right?
Yes. You link the thermostat application to your phone, and the system establishes an invisible perimeter around your property. When you leave work and breach that perimeter, say, when the GPS calculates you are 15 minutes away, the thermostat detects your approach and initiates a pre-cool sequence.
So instead of waiting until 5 p.m. when you unlock the front door, it starts the process early at like 4:15 p.m.
It gives the HVAC system a crucial head start. Because it has an extra 45 minutes, the system doesn't have to engage in a full-capacity sprint. It can run at a moderate stage, gently extracting the heat and humidity over a 90-minute window.
That makes so much sense.
By stretching the recovery load over a longer duration, the equipment avoids high-stress wear and tear. It consumes less peak energy and ensures the interior environment has already reached equilibrium by the time you step inside.
Taking advantage of humidity prioritization, multi-stage cooling, and geofencing really relies entirely on the specific hardware you install. We talked about the Nest earlier, which has a beautiful minimalist interface and that learning algorithm. But Dave Hotzel explicitly recommends the Ecobee for most of the home C services in Oklahoma.
His preference is rooted entirely in how different hardware handles the architectural realities of average homes. The Ecobee architecture utilizes remote room sensors rather than relying solely on the main wall unit.
Which directly addresses the systemic problem of the hot upstairs bedroom.
Oh, absolutely.
I mean, in almost every multi-level house, there is one room that bakes in the afternoon sun and sits 4 degrees warmer than the downstairs hallway.
If your only temperature sensor is built into a wall unit in a shaded downstairs hallway, your AC system is essentially blind.
It doesn't know what's going on upstairs.
Right. It cools the house until that specific patch of hallway drywall hits 72 degrees, and then it shuts off, completely oblivious to the fact that the upstairs bedroom is sweltering at 76 degrees.
It's maddening.
The Ecobee solves this sensory blindness. You place the remote sensor in the problematic bedroom, and the system algorithms can be configured to average the thermal data across the whole house, or to specifically prioritize the bedroom sensor during the sleep schedule.
It shifts the system's focus from a useless hallway to the actual room you are occupying. Dave points out that a central, single-point sensor like the standard Nest setup might be perfectly adequate for a smaller San Francisco condo with an open floor plan and uniform airflow.
Sure, in that specific environment.
But for the complex zoning issues of a sprawling, multi-level house in Kingfisher, Oklahoma, the Ecobee's distributed sensor network is a fundamentally better diagnostic tool for the HVAC unit.
It allows the schedule to dictate comfort based on actual human occupancy, rather than a single fixed location.
So what does this all mean for you? If you buy the Ecobee, deploy the remote sensors, and program Dave's central Oklahoma cooling schedule, are you guaranteed to see that 18% drop in your energy bill?
Well, the math will deliver the savings, provided you don't sabotage the system.
Sabotage the system.
Yeah. Dave highlights two fatal user errors that constantly destroy the carefully calculated efficiency. The first is what we can label the hold trap.
Right. Every thermostat has a hold button to manually override the schedule. Let's say you're hosting a summer gathering, the house fills up with people, the ambient heat rises, and you manually drop the temperature down to 68 degrees to compensate.
Dropping the temperature for a party is entirely reasonable. The fatal error occurs in the software settings.
Okay, how so?
Many users have their thermostat configured to maintain a manual override until they manually change it again.
Oh, no.
Right. They wake up the next day, forget they ever touched the dial, and the thermostat obediently holds the house at a massive delta T of 68 degrees for the next 3 weeks.
The automated schedule is permanently bypassed.
And the energy savings evaporate. The mechanical fix here is to dive into the settings and configure the hold function to expire automatically after 2 to 4 hours. You grant yourself the ability to adjust for temporary comfort, but force the system to revert back to the math.
That's a great tip to protect the system from human forgetfulness. What is the second fatal mistake?
Aggressive temperature swings. This happens when users misunderstand the diminishing returns of thermodynamics. They see that setting the away phase to 78 degrees saves money, and they incorrectly deduce that setting it to 82 degrees will yield massive profits.
Oh, I see where this is going.
Yeah, so they let the house bake at 82 while they're at work and then demand a drop to 70 when they get home.
A 12-degree recovery swing.
It is an insurmountable load. The energy savings curve severely flattens out once you push beyond a 6-degree setback. You save marginal pennies by letting it hit 82 instead of 78, but the recovery penalty is immense.
Because of the thermal mass, right?
Yes. When you demand a 12-degree drop, you aren't just cooling the air. You have to remove the thermal mass from the environment. The sofa, the drywall, the hardwood floors, they have all absorbed that 82-degree heat.
So the AC has to run at maximum capacity for hours just to pull the heat out of the furniture.
Precisely. That prolonged, high-capacity evening recovery effort mechanically chews up every fraction of a cent you save during the day. The golden rule of thermostat scheduling is to enforce a maximum 6-degree setback.
6 degrees.
Right. It optimizes the reduction in heat transfer without creating an unmanageable thermal mass penalty for your equipment to overcome.
To summarize the core realization here, the smart thermostat mounted on your wall is just a user interface. It is a screen and a relay switch. The true financial return on investment lives entirely inside the schedule.
If you don't build the parameters, the hardware cannot execute the savings.
Yeah, it's entirely dependent on the instructions you provide. And we really have to give full credit to the source of this blueprint. If you are listening to this in the Kingfisher, Canadian, Garfield, Logan, Blaine, Major, or NW Oklahoma County areas, Dave Hartzell at Hartzell's Heat and Air is the definitive expert.
The guy knows his stuff.
He really does. You can find him at hartzellsheetair.com. or call 405-375-4822. Dave actually configures these specific optimal schedules for free as part of any service visit or new install. He makes sure the digital hardware communicates correctly with the mechanical equipment.
You know, we buy smart technology expecting it to possess its own wisdom, to just automatically fix our problems.
Right.
But as this deep dive shows, smart really just means obedient. If a smart device is failing you, it might simply be because you haven't given it the right instructions yet. It makes you wonder, what other smart devices in your life are quietly costing you money right now, just sitting there, waiting for you to tell them how to actually be smart?
That is a very dangerous question to ask. I'm going to be staring at my smart fridge all night now, wondering what it's plotting.
Yes.
But it perfectly circles back to that homeowner in Hennessey. Don't let your shiny new gadget cost you more than the dumb one it replaced. Take 5 minutes, build the schedule, and let the thermodynamics do the heavy lifting. Thanks for joining us on this deep dive.